basically if we have as much we need perceptrons, we can make any classification function with those perceptrons. Yeah? So we just need to put them in the right order and then use right weights in order to make any classifier that we want. And even if we want to just design a function which is continuous, like what we have in regression, we are not classifying, but we are just learning a continuous function, a real valued function, then we still can do it, only we do approximation. Yeah? And when we have infinite number of perceptrons, then our approximation is very accurate. And this is where we ended up last time. So if I have any functions, function g is any function that you can think of, but assume that this function is a kind of nice function. Yeah? So under a kind of regularity constraint, so the function is not crazy going up or down. So if you have any good function, then you always can make a perceptron, a network of perceptrons, or what we from now on are going to call it a neural network. So if we just put all of those perceptrons next to each other, then there exists one configuration for those perceptrons, meaning that we have specific configuration specified with the hyperparameters h, and also specific weights specified with the w, that this new model is going to be exactly same as the function that we are targeting. Yeah? And if we look into like any argument and then we just calculate the maximum possible error that we get with this approximating function, then we're going to see that that one is small enough. So if you tell me that I want to make this function or this model, this network of perceptrons, very close to this particular function, so you give me the epsilon, then I'm going to just ask you for too many perceptrons. So I would say like I need 10,000 perceptrons, and I'm going to do that for you. Yeah? And then this simply means universal approximation theorem. So as I said, we are not going to play around with this theorem a lot because this is basically not the part of deep learning course, but this is a kind of motivating point where lets us to just start with neural networks. Okay? So the point here is that neural networks, even with simple perceptron next to each other, they are very powerful. They can make anything that we want. And anything that in the nature that exists at the end of the day is a function. Yeah? So there is a bunch of input into it, and then you want to see what is the output. And whatever that function is, it doesn't matter how complicated that is. We can, at the end of the day, learn it by a network of artificial neurons. So that's going to take us into the formal introduction to neuron and neural networks. Yes?
Yeah. In the last slide, you said that our function would be a good function.
Good function.
Yeah, and if it wasn't a good function, and for example, we have something like delta or something like that.
Yes.
Is still this theorem?
I mean, yeah, this g here, I mean, a good function, I don't necessarily mean this is continuous or bounded. I guess you need this to be bounded. So pretty much I can say that if it is not bounded, then you cannot easily do that. Yeah? But if it is bounded, which is always the case, being bounded simply means that your output is always some bounded value. Yeah? Which is usually the case in practice, then that's fine. Yeah, it's a very, very big set of functions.
Yeah, so is there any, for example, formal condition for it?
Yeah, sure. I mean, if you check the papers that I put in the further read, you're going to see. So this was proved somewhere around, I think, 80s or 90s. And then there had been like different versions of it. So the most recent version, I mean, most recent like 20, 30 years ago, I think it gives you the most general conditions that you can think of. Yeah, you can check it, of course. Yeah, so this is going to take us, as I said, into the introduction of neural networks. And to introduce the neural network, we need to formally introduce an artificial neuron. So what is artificial neuron? Basically, it's the perceptron with this difference that instead of having a step function at the output, we can put any function there. Okay? So I have a bunch of inputs, so say n-dimensional data points. So I give it to a linear model. I have a bias as well. So this is going to be an affine function. I calculate this affine transform z, which is a single number, and then I give this single number to one activation function. Yeah? So in the perceptron, you had the same thing. This activation function was a step function, right? But you can think of any activation function. And this is what we call it artificial neuron. So many people call this still perceptron. That's fine, but this is not what perceptron was initially. Okay? So I would rather call it artificial neuron. Yeah? Now, what I'm going to do from now on is that instead of showing like this, I'm going to do the same trick as I did with perceptron. So I'm going to show it as a node here. And then I write down f inside it, which is my activation. Yeah? So that's going to be my neural network. You do know what it does. Yeah? It's going to take the input, going to do a linear transform on it, and after that, it is going to just pass it through that activation function. And of course, any single neuron going to have n plus 1 learnable parameters, right? So when you have n inputs, for every input you have a weight, so n weights, plus 1 bias is going to be n plus 1 learnable parameters for every single neuron we're going to have. So what I'm going to do from now on is also that many times I'm just dropping these w's and b. Yeah? I simply show those links. And you do know from now on that those links simply means weight. Yeah? Clear? OK, cool. So that is an artificial neuron. So if I want to write it down mathematically, I would say this output is the activation function of z, right? So y is going to be the activation function of z, or what I'm going to call it from now on, activated version of z. And what is z? Z is the linear transform of your input. So x goes in, you calculate this linear function or affine function, you activate it, you're going to get your output. Yeah? So again, here w is the weight vector, b is the bias, f is the activation function. So it could be any function here. You can consider any function. And perceptron is a special case where this function is the step function, right? Clear? Cool. Now, one other special case we had before, and that is when I set this function f to be the linear function, right? So if I set f to be exactly itself, so line, activation function is now a line, then what would be this neuron? Is the, you know it, just say it, don't worry. It's the linear model, exactly. So this guy, if I drop f, so if I set f to be the linear function, then this artificial neuron is going to be the linear model, the one which we use for a dummy example, right? So linear model, perceptron, they are a special case of this guy. And in general, you can have any function, and then it's going to be artificial neuron. But if you really want to have a neural network, then you need to have neurons which have nonlinear activation functions. So in assignment 1, you're going to see that if you just replace a linear function here, it basically means that you're doing nothing. Yeah? So if you just put lots of neurons, all of them with linear activation, it means that you are cascading lots of linear models. And at the end of the day, they all add up to be just one linear model. So you're doing nothing then. So moral of the story, having nonlinear activation function in practice is very, very important. Yeah? So you need to have nonlinear activation. And it doesn't matter really what the nonlinear activation is. As long as it is nonlinear, then that universal approximation theorem is correct. Okay? Now, what are the papular activation functions? So the first one is ReLU, rectified linear unit. And this is basically a linear function. So as you can see, when x is positive, then it is a linear function. But when it's negative, it's going to be 0, right? Clear? And you can write it down in this form, of course. It's a ReLU function. So it's the maximum of x and 0. If x is negative, the maximum going to be 0, so you're going to be 0. If x is positive, the maximum going to be x itself, so it's the linear function. Clear? So that is the ReLU function. One other guy is the sigmoid function. And this sigmoid function, you can write it down in this form. So it's going to change from 0 to 1. Yeah? And you can simply see it here. Just look at this guy. If I put x, if I send x to be plus infinity, what's going to happen? This e to power minus x is going to be 0, right? And then it's 1 over 1, it's 1. So it's the top one, yeah? Then if I reduce x from plus infinity, it's going to gradually reduce. If I put it 0, if I put x exactly 0, what is going to be? 1/2, exactly. Because e to power 0 is 1, it's 1 over 2, it's going to be 1/2, right? So it's going to cross this line or meet the vertical axis at half, and then it's going to gradually go down. And if I send x to minus infinity, what's going to happen? It's going to be 0, because e to power minus minus infinity is e to power plus infinity. It's infinity itself. 1 over infinity is 0, right? So starting from 0, you gradually go up. You hit the vertical line at half, and then you go to 1, right? So it's like the step function you had for perceptron, right? But now you're just making it smooth, right? So there you were just hardly jumping from 0 to 1. Now you are just gradually jumping from 0 to 1. So that is the sigmoid function. You can have tan h function. So this one is like, all of you know it. So it's basically a hyperbolic function. And then you can simply check that when you put x 0, this is basically 0 because it's 1 minus 1. If you send it to plus infinity, then it's going to be 1. And if you just send it to minus infinity, it's going to be minus 1, right? Minus infinity, yes, it's going to be minus 1, right? Yeah.
In sigmoid function, why do we use e? Why don't we use, for example, 2, 3, some other number?
What do you mean by 2, 3?
No, we have e in the
Exponent, yes.
exponent. Why
Exponent.
don't we use, for example, 2 or 3 instead of
Ah, I see. No specific reason, I guess.
in previous function, ReLU?
Yeah.
What is the motivation behind, for example, doing this?
Because this is the minimal nonlinearity you can make.
For example, why don't we use, for example, something like this, absolute value?
The absolute value, yeah, I mean, this comes from the motive that if you think in terms of universal approximation theorem, then what you can do is that just say you have the whole plane, yeah? And then what you want to do, you want to make a specific diagram inside it, yeah? What you can do, you can always rotate that, and then you cut the negative part, yeah? And then you keep the positive part, okay? And then if you do this, you're going to make any architecture, any diagram from the plane surface, right? So this was the initial motivation, I guess, that people started to consider ReLU. But down the road, the main reason is that it's a minimal model for activation, first of all, and secondly, it works very well in experiments, okay? So absolute value, I think you can do it, but it's not as good as that one because it could put you into some sort of instability. Yeah.
Sorry.
Yeah.
It works very well. I also saw that in multiple problem that people use ReLU.
Yeah.
And I always wondering why this function works really well. What's the theory?
This is exactly the one that I told you. So say, I told your friend, sorry. So if you have, I mean, I don't want to confuse you with that, but let's say I have this surface, okay? And I want to make out of it some shape, like this guy, okay? The thing that I can do, I can rotate it a bit. Yeah? Maybe this is not the best shape that I'm thinking of, I don't know. Maybe I want to make this triangle, yeah? I can shift it a bit, so if you think of this as coordinate, so I can just shift it a bit, so when I shift it right, So say, for example, sorry, this is something like this, then I can always just cut the negative part, yeah? So if I cut the negative part, I'm getting to get this shape, yeah? And then the next time I again shape it, rotate it, and then I just, I don't know, cut it in other form. So maybe this time, so I'm bad in painting, but I don't know, maybe this is gonna be something like this. And then I'm going to again cut it in the negative parts, meaning that I'm gonna get rid of this. And gradually I'm going to make any shape that I want. So if I want to do this, I'm not smart enough right now, but you can just rotate it and always cut the negative part until you get into that one, okay? And if you can solve this problem, so if you can get from the pure surface, like plane surface, into any shape, then this means that you are doing the thing that you do in universal approximation theory.
And that's what we exactly told about perceptron. Am I right?
Yeah, no, but in perceptron you don't keep the right one. You just replace the right one with 1, right? So look at ReLU. If you give x to it, you keep x when it's positive, right? This is the difference with perceptron. And the key point here is that ReLU is a continuous function. So when we start doing optimization, you can deal with that. We cannot deal with perceptron, the step function. Yeah? But yeah, it's the same thing conceptually as we do with perceptron. So there also, since we can just write down anything in expansion of pulses, then we can do the same thing. Yeah. Any other question? Okay, so ReLU, sigmoid, tanh, and there is also a soft version of ReLU. So it's basically the approximation, the smooth approximation of ReLU. And this is what basically it does. If I send x to minus infinity, what's going to happen? If x goes to minus infinity here, what would be the output of this function? It's going to be 0, yeah, because x is minus infinity, so e to power minus infinity is 0. Log of 1 is 0, right? Now, if I send x to be plus infinity, so if I assume that x is much, or e to power x is much larger than 1, then I could say 1 plus e to power x is approximately e to power x. And then if I calculate the log of this guy, it's going to be x, right? So then soft ReLU, or I have shown it by SR ReLU, then it's going to be simply approximately log of e to power x, which is x itself. So it's basically a ReLU in extreme case, but in between, close to 0, it's not ReLU, which gives you a continuous and differentiable function, right? Clear?
Does the activation function always need to be differentiable?
Differentiable, not necessarily, but we're going to see it. We need to have it continuous. It doesn't mean that we cannot deal with non-continuous activation functions, but when we start training our model by gradient descent, then it's going to trouble us. It could trouble us potentially. Is the best thing you could have. If you don't have differentiable like ReLU, still if it is continuous, so you don't have any jump in the function, it's still fine. Yeah? We can use subgradient. But if we have totally discontinuous function like a step function, then we cannot really use the basic form of gradient descent. We need to just use the sign, and it could take us into trouble. Okay? So the less singular everything is, the better it is for you, because at the end of the day, you can use gradient descent more efficiently. And this is the only thing that you can use to train your model. Yeah, we see it. We see it. Yeah, of course. Yeah. Yep.
I have the impression that the activation functions are all like try to be like the step functions, so they're like increasing.
No, this one is not trying to be a step function. So these are two different classes of. So this guy is just, it could go to infinity. It's trying to just approximate non-linearly the linear function. Yeah, this is one class, and this is another class which is trying to just approximate a step function, which is popular for classification, as you're going to see, because it can give you a sort of probability distribution.
So can we have like a decreasing activation function?
Oh, decreasing activation function. So that, I mean, depends if you negative everything, like if I negative everything here, so it's going to be decreasing, and I don't think that it's going to trouble you. So yes, but there is no reason to do that. Yeah. But this is possible, I guess. Yeah. So any other question? Cool. So that was it. So you do know right now what is an artificial neuron, and then a neural network is basically a collection of these artificial neurons. So if I want to officially define a neural network, so one artificial neural network is a directed graph that connects a bunch of inputs into a bunch of outputs, right? So I have a bunch of inputs, x1, x2, so my input has basically 2 entries, and I have one single output y, and what I want to do, I want to connect it to that one, so I'm going to use a bunch of neurons. So I get basically x1 and x2, I give it to one neuron, it's going to give me a bunch of outputs, then I pass them to another neurons, and I do it till I get to the output. So anything of this form, any graph you draw like this, and you treat everything in between to be an artificial neuron, is a neural network. Clear? Now, from now on, I'm going to call it neural network because we all do know that they are artificial. Yeah? So no ANN anymore nowadays, so it's a neural network. Right. So now, depth of a neural network. You can define for your neural network depth. And the depth is basically the longest distance that you should take from one input to get into the output. In other words, if you think of this architecture like being a kind of transform of information from x1, x2 to your output, depth basically tells you what is the longest way that your information should pass in order to get to the output. Like, look at this guy. What is the depth? 3, exactly. So the longest one is the one I showed with blue. I mean, of course, you could have other long distances, like x1 to f3 to f1 to f4. This is again 3. But you do also have path with length 2. So here x2 to f1, f1 to f4. You see it? So the longest path is your depth, right? No.
Where are we dropping the edge from f4 to y?
Sorry?
From f4 to y, there's another edge.
Yeah, that is not because this is a link from one neuron to another. Yeah, that is output. I'm just indicating this is the output. So this is not a link. Yeah, but once I just in one slide, you're gonna see it. You're gonna get it clear. Okay. So now, as you said, the depth here is 3. Okay, so hopefully it's clear. Yeah. Now, what is a deep neural network? A deep neural network is any neural network whose depth is larger than 2. 2 not included. Yeah. Anything larger than 2 is a deep neural network. And you might say, oh, this is not that deep, and you're right. Yeah. So anything which is deep, it's not shallow, is called a deep neural network. Now, this example is basically a deep neural network. Okay? Clear? Because you have here depth 3, and 3 is more than 2, so it is a deep neural network. Now, this is a nice thing. You can write it down in form of graphs, things like that, but at the end of the day, we are always dealing with layered architectures. And what is a layer? So a layer is basically a set of neurons which are in the same distance from your input. Yeah? So what do I mean? I start with my input, and then I take a bunch of neurons in one layer. I stack them together. I connect maybe all of them, maybe some of them, some of those inputs, to these neurons. And then if I want to process further, I get the output of those neurons, and then I connect them to another bunch of neurons. Yeah? And each of these each of these stacks of neurons is called a layer, right? And then you have multiple layers till you get to your output. Clear? So this is now the typical architecture you always think of when anyone tells you about neural network, right? And then in this layered architecture, what we do have, we have three different types of layers. The first type is the one which is at the input, and we call it input layer. Yeah? So the first layer is the one which includes x1 to xn, but one thing important here is that that input layer has no neuron, right? You got it? Clear? So there is no neuron here. It's your input, yeah? So those numbers, those pixels of your image, they are the one which are at the input, yeah? And they are getting connected to the first bunch of neurons, the second bunch of neurons, and so on till you get to your output. Clear? Yeah.
Yeah, I have a question. I know that whenever we increase the depth, it would be a better network for us.
You're right.
It works better.
Yeah.
I was wondering, if we dense each layer, is it still a good option?
What do you mean by density?
In a layer, we increase the number of...
Yeah, sure. You're going to see it in the first assignment. I mean, there is a kind of trade-off, but you always want to go for deep neural networks. You never want to do that. Because, put it simple, like if I want to just make one function, and if I want to do it with only one layer in between, then I need maybe, I don't know, 10,000 neurons. But if I want to do the same function with multiple layers, then instead of 10,000, I can have only 1,000 neurons. So I can drastically reduce. I mean, it's exponential reduce in terms of the number of neurons that we need. And this is the main reason we always use deep neural networks. But you're going to see this in your first assignment. So there is one particular example where you want to just realize one binary function. And if you do it with one layer, you're going to need exponential large number of neurons. But if you do it with a deep neural network, then you just need a linear number of neurons. No, we don't have, but we have very large number of neurons.
Yeah.
So it's in the order of 10 to power, I don't know, 7, 8 at least nowadays. Yeah.
Okay, thanks.
Yeah, no worries. Yeah.
Is it always the case that, so there are capital N neurons in the input layer, or there are circles at least.
Yeah.
And then for the first layer, second layer, etc., does it always increase?
No, there's no reason. So, I mean, you're going to see it later, but it depends on your problem. I mean, typically, if you want to extract too much information, you usually do that. So you start from your dimension, you try to expand to just grasp all possible information that you have. Then you start to just reduce, because you're going to say, okay, now that I have all the features, now I'm going to filter them out. Yeah, but you don't need to worry about it right now. You're going to get it in future. I mean, at some point, you're going to see it immediately. Okay? But there is no reason. I mean, theory, you can have like just one neuron here. I mean, just think of perceptron. Perceptron, I mean, how many, it doesn't matter how many input you have, you always end up with one neuron. Yeah? No. Any other question? Yep.
Can we use different activation functions?
Of course, yes. You can use different activations. Yeah, of course. Any questions? Cool, great. So this is the input layer, and then we got one output layer, and the output layer is basically the layer which includes the output neurons. And what do I mean by output neurons? I mean the neurons which you look at their output and you take it as your output that you want, right? You take it as the label that you are predicting. Clear? So that is here the output layer. And anything in between these two is what we call it a hidden layer, right? Because it's hidden from the eyes of the one who gives the input and who takes the output, right? Now, if you look at this layered architecture, and I want to just calculate the depth of this architecture, what is the depth of this in terms of the number of layers that it has? No, not this particular one. Say I have number of hidden layers. Now, yeah? What is the depth? Plus 1. Great. Okay. So the depth of one architecture neural network, it's going to be the number of hidden layers that you have plus 1, and then 1 is your your output layer. Clear? Now, this is going to be the depth, and then if this is the depth, then what is a deep layered neural network? The one which has more than one hidden layer, yeah? 2 or more, right? So if you have more than one hidden layer, then you are dealing with a deep neural network. Clear? So anything with more than one hidden layer is a deep neural network. So it doesn't really need to be that deep, yeah? Clear? Good. So this guy, this is what we did to realize the XOR. And it is a neural network. Why? Because we have a bunch of perceptrons, and perceptrons are artificial neurons, right? Now, here if you look at this, what is the input layer? Can you tell me? X1, X2. This is the input layer. What is the output layer? Yeah, this one. This single perceptron which calculates Y, the AND for you, yeah? And what is the hidden layer? These two guys in between, yeah? They make one layer, and this is the hidden layer. Now, is it a deep neural network? No, this is not a deep neural network because we have just one hidden layer, right? And then it is not a deep neural network. Usually we call it a shallow neural network, okay? When it's not deep, it's shallow. Clear? So that's it about the definition of neural networks. But now that we have the idea of what neural networks are, then the question is if we want to talk in language of machine learning. So what is a neural network? It's basically a model, a parameterized model, right? This guy, if I think of all of these edges as weights and all of these guys here as biases, then this is basically a parameterized function. Yeah, I can write it down from input to output. And there are a bunch of parameters here which I want to learn, right? So it's at the end of the day a model, but the model has this cool property that it's I can expand it, yeah? So if I'm not happy with this model, I can add one layer, yeah? I can increase the number of neurons in one layer, right? So this is the key property of this function or this model. And another key property is that based on universal approximation theorem, I do know that if I just make it deep enough, large enough, then I'm going at the end of the day to learn any function that I want. So there is a kind of theoretical guarantee behind using this model. This is the second reason. Now, if I look at this guy, now I want to first of all know what are the hyperparameters, because we said if you have a model, then we have a bunch of hyperparameters. And back to then when we started with perceptron, we couldn't really talk about hyperparameters because I told you simply just think of that step function as a hyperparameter. Here you have more hyperparameters, yeah? What is your depth? How many layers you're using? This is your choice, right? So it's a hyperparameter. What is the width, number of neurons within every single layer? It's again your choice, so it's a hyperparameter, right? So these are now your hyperparameters, number of neurons that you have, how you connect them together, the depth of that neural network, the kind of activations you are using. These are all sort of hyperparameters that you're going to decide based on probably your experience before you start training that model, and they are all hyperparameters, yeah? And what are the learnable parameters? What do you learn? The weights and biases, yeah? So this is what I told you at the very beginning, that at the end of the day you are always learning a bunch of weights. Clear? So the weights and biases are those parameters that you are supposed to learn. Now, if you do know one architecture, and by architecture I simply mean that I think it's clear right now for you, that I just tell you how to put the neurons and how to connect them. So if I decide on one architecture, then I can really count the number of parameters that I need to learn, right? So for example, here in this dummy example that we had, I have 4 different neurons, right? So the first one is activated with function f1, and then this one f2, f3, f4, yeah? So this is a kind of hyperparameter that I have decided for those functions. Another hyperparameter is that I have decided for this particular architecture. So I decided to connect my input in this form to f3, then f1, and so on, yeah? But once I give you this guy, then you can tell me how many weights and biases I have here, right? For example, let's look at the neuron 1, 2, 3, right? So this neuron 1, 1, 2, 3, sorry for that. So 1 has 2 different inputs, right? Clear? So how many parameters does it have? 3, yeah? You have 2 weights because you have 2 inputs. Each one gets multiplied with 1 weight. And then you have 1 bias, right? So this guy is going to have 3 parameters to learn. What about F3? The same, right? It has, again, 2 inputs. Each of them is a weight, a bias. So you have 3 parameters. Same is for F2, yeah? And what about F4? 5. It has 4 different inputs plus a bias. So you're going to have 5 parameters. And then you can just do the calculation. So you have 14 different parameters, 14 different weights and biases that you need to learn, yeah? So at the end of the day, you're going to write down a loss function, or use your loss function to write down an empirical risk, and that empirical risk is a function of these 14 different variables, and you need to solve an optimization problem which gives you the minimum empirical risk, right? Clear? Any questions? Yep.
Do we have any analytical methods or mathematical methods to use the optimum number of neurons, layers,
Oh,
or
that
something
one.
like that?
No, you don't have it. I mean, you can formulate it, but mathematically it's too hard to solve it. So you can do a kind of what people call it like two-tier optimization. Like you can think of your hyperparameters again as a parameter, and then when you do optimize the inner loop, then you want to optimize the outer loop as well. But this is like infeasible to compute. You could never do that. Of course, you can define it, like there exists that, but you can never compute it. Yeah. Any questions? Cool, great. So now we got into deep learning, so we are now ready finally to get the deep learning defined. So deep learning is basically machine learning when your model is a deep neural network. Yeah? When you are using a deep neural network as your model, then it is deep learning. That's it. Yeah? So nothing coming from Mars, right? And in machine learning, when we talk general about machine learning, what is that? That is like we are training any model on any data set, and we consider general laws. But then when we come into deep learning, we are just focusing on deep neural networks, right? And then in between, I told you also something called representation learning, and I told you good news, you don't need to worry about that. We're not going to study this. So representation learning was the story of machine learning, but then they were looking into a specific kind of models. So the models which are written in form of some kernels, yeah? And we don't need to think about them because a very special case of representation learning is that we put the model to be a deep neural network. So deep neural network is one of the kind that was considered in representation learning, yeah? And then at some point people were thinking maybe we should think general, like in representation learning, but then it turned out that deep neural networks are fine enough to do anything that you want, yeah? So the moral of the story, when we talk about deep learning, we are talking about a very small subset of representation learning. And that guy itself is, again, a subset of machine learning. Yeah? And what we are going to do in this lecture, we just focus on this subset, because we do know this is the good subset of the approaches that we can do in machine learning. Yeah? Clear? Yep. Representation learning, I mean, here in deep learning, you consider deep neural network as your model, right? But why should it be a deep neural network? Yeah?
Can be not layered, not structured.
It's again a sort of structured model, but instead of just having artificial neurons as your components, you have a kind of weird, nonlinear, multidimensional function. Yeah? And then that weird thing, which is not an artificial neuron, so it's not simply a linear thing activated, but is a kind of more general form. And then that one is a kernel. Okay? And then the question back to them was that what is the good kernel? Yeah? So you can think of deep neural network as a kind of representation learning model whose kernel is this artificial neuron. So put it simple. Okay?
Okay, I kind of got it. So if you fix the model as a deep neural net that has layers and more than 2 billion layers, then we're in the deep learning territory.
Yes,
but
exactly.
we still have freedom over choosing arbitrary laws.
Exactly.
And
Arbitrary data set. Yeah, of course, data set is given to you, but arbitrary loss, of course. And you design the loss for your problem, of course, definitely. Yeah. Any questions? Cool, great. So that's it about deep learning. So now deep learning is over, and now the story starts with how we can deal with this training of the model, right? So up to now, what we do know is that we basically have 3 different things. So data set, model, loss, and then if we are talking about deep learning, we basically focus only on deep neural networks. And what we want to do, we want to do the training, and training now simply for us means that we want to find the right weights and biases in the deep neural network that does the job, minimizes the empirical risk for us, right? So this is it. I mean, that's over. If you just wanted to know what is deep learning, that's it. Yeah? So not very complicated thing. But the whole complication starts with the fact that we want to really make them work. Meaning that we want to know, first of all, how we can minimize this empirical risk, which from perceptron algorithm, you do know that it's not an easy thing to do. Yeah? Especially if you think of like having too many perceptrons, packed together. This is one thing. And the other thing is that even if I know how to do it, what is the right architecture that I should use? Yeah? What should be that activation function? How many neurons should I put there? And how should I specify each layer? And how I should make those layers connected and things like that. So this is what we are going to learn through the semester. So we start with feed-forward neural network, then convolutional neural networks, and then recurrent neural networks. So all of them are basically artificial neural networks, but each of them has a specific property. Yeah? You connect them differently, you activate the things differently, and so on. And then for each of them, we are going to learn how we can do the training. But the training is a kind of general thing which we apply it to everyone. So now that's it for the deep learning part. And then what we should start with now is to just understand, first of all, how we can do the training, meaning that we learn how we can minimize the empirical risk. And this is why we need to have a very short introduction to function optimization, which we kind of have it after 5 minutes only, please. Break. Yeah. See you in 5 minutes. So, shall we go on? Yep. So, function optimization. So, this is something that pretty much we're doing from now on. Yeah? So, we basically do know what our problem is. I mean, we have a deep neural network, we have the empirical risk, we want to minimize it. And of course, the only tool we need here is the kind of algorithm that we can use in order to optimize or minimize our loss function, or risk function, sorry. So if you look at this optimization here, so this is what we call the training process. So the training process was that we minimize this empirical risk, which is written in this form. If we just want to recap what are every single element in this argument, so we can simply start with this f. So f was basically the model that we had. H was the hyperparameters. We said that we right now do not do anything about hyperparameters. We think they are fixed, given to us. And then the next thing is this w, which is the vector of learnable parameters, or basically the weights inside our neural network. So when we are talking about a deep neural network, then we basically have a bunch of weights and biases, all of them collected inside this w, right? So if you think of that dummy example I gave you with 14 different weights and biases, this w is basically one vector of size 14. And the first one is, for example, the first weight of the first neuron. The second one is the second weight of the first neuron. And you keep on going till the last parameter, right? So this vector w is basically collecting any weight and bias you do have in your architecture. And x is basically the data point that you have inside your data set. And y is its corresponding label. And I is the number of points you have inside your data set, the number of samples you got. Yeah? And you construct this empirical risk. At the end of the day, when you do the summation and everything, you remain with a function which only depends on w. And it doesn't matter. Sorry, I forgot. An L here is, of course, loss, which is the loss between the output and the label. And it really doesn't matter which kind of loss you use or which model we are having. At the end of the day, we end up with one function. And that function is only depending on the weights, right? The parameters. And we want to minimize this function. Yeah? So for now, for these remaining slides, you can forget about anything above, and you can only think of minimizing a function. Yeah? If you do find a kind of algorithm which helps you minimizing a function, then you can simply use it for your training, right? So this is why I'm going to stick to that one. So I'm going to stick to this empirical risk. And what you do know is that in practice, when it comes to deep neural network, that w has, I don't know, 10 to the power 8 different parameters inside it, right? So it's a very huge function. But just for sake of simplicity, just that we can draw everything down, whenever needed, I always think of this function to be either one-dimensional or two-dimensional, yeah? But you should always expand it in your mind about like multi-dimensional thing, yeah? Good. So if you have one function like that, and this is your empirical risk, that guy could have local and global minimum, yeah? And what is a local minimum? What is a global minimum? Global minimum is basically the point which is below every guy, yeah? All across the axis, right? And then you got this local guy, which is minimum in the neighborhood, yeah? So when you are at this point, any guy around it is larger than this one. But you need to just take a bit of tour outside this point till you get to a better minimum, yeah? Now, when we are training our model, what we are looking for, we hope that we get this global model minimum, right? So we hope that we get the point, the set of weights, which gives us exactly the minimum possible risk. But in practice, we usually are happy if we end up with some local minimum, yeah? Meaning that at least around it, the other possible weights, we are doing fine, yeah? Because as you're going to see, it's pretty much impossible to guarantee getting into that global minimum unless you have a very simple risk function, which is not the case. Okay? So, yeah.
What does it mean for the loss to be negative?
I mean, if you think of it like there are losses like cross entropy potentially could be negative. Let me think how I define the cross entropy. Yeah, I think it could be negative. Or no, I think no, that is not negative, so the binary one. But you can define the base loss, for example. There are losses. I mean, if I have one loss, like say the MSE loss that we defined it, yeah? So then if I just get one big negative number and add it to that MSE, and I minimize this one, it could still train my model, right?
Isn't MSE like square?
Yeah, square, that itself is positive, yeah? But then I define a new function, which is that one plus a very big negative. And minimizing that one is no different from the previous one, right? Yeah. So you could have negative loss, but for most examples that you think of, it's not negative, of course. Yeah. Okay. Any question? No question. Okay. So then, one thing that it comes to your mind, I'm pretty sure it doesn't come to your mind. It probably has come to my mind when I was at your place because I'm not smart enough. So is that you might say, okay, I mean, I want to just minimize this guy. Yeah? I want to find the minimum point on this function. So why should it be a big deal? Because I can just grid the axis. Yeah? So I could say, okay, this function is usually somewhere between 0 and 10. And then I make, I don't know, 100 points in between. And I check the value function on every single point. And then I take the one which is minimized. Yeah? I can do it with that search, right? Clear? So I got this function. So here is W. Here is your risk function. And then I do know, for example, W is changing between 0 and 10, for example. Or I don't know, 0 and 1. And then it is like this. So I don't know, like this. And then I'm going to say, okay, I'm going to just grid this axis. So I'm going to say this is the first grid, second grid, and so on. And I keep on gridding it, yeah? And then I start from the first point, center of this grid, center of this grid. I calculate the value of the function, right? And then this grid is going to give me some very small number. And after just searching over everything, then I'm going to say, okay, this is the minimum number I could get. So this is approximately W star that I am looking for. Clear? So I could do it, right? And if I want to do it on this function, I just need, I need, I don't know, 10 grids. Yeah? Say, for example, I don't want to be very accurate, so I just need 10 different grids. Yeah? So I just search among 10 numbers, and then it's going to be, I'm going to find approximately the minimizer. So why it is a big deal? So the point is that, as I said, you should always think about a high-dimensional thing. Because what happens if my function is two-dimensional? No? What happens if my function is two-dimensional? In that case, W space is like this. Yeah? So it's going to be W1, for example. This is W2. And then you get your loss function, which is a surface in this, two-dimensional space. I mean, a three-dimensional space. I'm sorry, I'm very bad in drawing things, but I hope that it's clear enough. Yeah? So you have a surface, and then if you want to find the optimal one, what should you do? You should grid this guy with 10 points, right? And you should grid this axis also with 10 points, right? And how many points going to be in between that you should check? 100, 10 to power 2, yeah? Now, let's expand it. If I have a model, so d-dimensional model, yeah? Yeah. So I assume that this W has this W vector has d different parameters inside it, right? Now, if I need G grid points, so G is basically that 10 number I told you. If for every axis I just want to have a grid size G, how many points at the end of the day I should search? g to power d, exactly. So I need to search g to power d different points, right? And this d, I told you, it is in the order of 10 to power 5, 6, 7, yeah? So very easy case, you have 10 to power 5. 1, 5 numbers right in front of it, right? Yeah? So you need, if only for 10, a grid size of 10, then you need to search 10 to power 1, 1, 2, 3, 4, 5. This much of points. And I don't think we can do it, huh? So this is why the optimization problem is challenging. As I said, most of you know it, but just for those who are at my level. So this is a very complicated problem because this is exponentially large number of searches. Yeah? So I need to search over exponentially large number of points in order to find my minimizer. So basically I cannot do it by simple search. So what I told you here is what we call it exhaustive search. Yeah? And it's impossible to do it, especially when it comes to minimizing a risk function. Yeah? So what should I do instead? I should go for something that people usually call an optimization algorithm or optimizer. So what is an optimizer? It simply starts from one point on the function, and somehow it finds out which direction it should go in order to make the function smaller and smaller. Yeah? So you start from one initial point, then it somehow decides on this function, it says, okay, if I go right, then I'm going to get smaller value, right? And then it just move right, yeah? So in each step that it takes, we want the empirical risk to get smaller and smaller. And one thing else that we don't want this guy to go forever, yeah? We want it to stop at some point, yeah? So the next thing is that, we take a certain number, a finite number of steps. That finite number could be large, but it should be finite till it gets somewhere that it stops, right? And hopefully that point that it stops is some sort of minimizer. So it's at least a local minimizer of the function that we are minimizing. Clear? So this is what we call it an optimization algorithm or optimizer. Yeah? And we can always write it down in this form of pseudocode. So we can start with some initial points. So this is W0. So this is in the first very initial iteration. So randomly you choose one point. And then what I'm going to do, so that delta that you see is infinity is a kind of stopping criteria. Yeah? So as long as delta is more than some epsilon, some very tiny number, I'm going to keep iterating. I'm going to keep going forward, right? And initially I put it to plus infinity because I want to get into the loop, right? So I'm going to get inside this loop, and what I'm going to do in the loop, first of all, I just make some sort of magic. This is what we are going to do in gradient descent. Yeah? I'm going to find some way that it tells me which direction, which step size, and which direction I should take in order to make my function smaller. And let's say that guy is the mu vector. So mu vector is basically the same thing or in the same space as this w. So if w is a scalar, mu is again a scalar, right? And this scalar is potentially a small scalar, but it's telling us if you add me to your previous value of weight, then the next value of weight is giving you a smaller risk, right? Clear? So this is the next thing I want to do. And after that, I am going to update my stopping criteria. So I'm going to look at this new value of my risk. I compare it to the previous value. And if it's like a good drop, I keep on going, right? And I keep on going till I'm not changing at all. Yeah? So it somehow is showing this guy, yeah? Because we started here from one point. Then mu is that tiny move forward. It tells us go a bit forward, and then when I do it, I drop in the function. Okay, it's the right way to go. Keep on going, yeah? I again go a bit, yeah? And I'm again dropping. And I keep on dropping till at some point I'm not changing anymore, yeah? So if I go forward with a very tiny step, nothing is changing. Then I stop, yeah? Clear? Yeah?
The mu is a direction or the...
Direction.
Is that the learning rate or
No, it's not. We're going to talk about this, yeah? But it's a direction. It's a vector, a very tiny vector, moving towards the direction that is the right way to go. You got it, good?
Yeah. So on the previous slide, you have like plus online. Right?
Here?
Yeah, plus mu.
Yeah, we will.
Minus?
Then you're going to be minus gradient. I do know what you're thinking of, but no. Right now, you're going to find out that mu should be minus your gradient.
I see.
Yeah?
Right.
Okay.
You didn't unpack it.
Yes. Okay. Any question? So you got the idea of what is the optimization algorithm we are looking for, yeah? And now the only question there is that what is this mu? How we can find this guy out, yeah? And of course, these are the favorable things that we are looking for. First of all, in this line 5, we hope that each time we update, most of the times at least, we are just dropping in the value of the loss. This is one thing. Value of the risk. And the other thing is that we're going to stop. I mean, this loop going to stop at some point. We're not going to just iterate forever, right? So these are what we are hoping for. And the answer to that is that this guy, this mu guy, is basically negative sign of the gradient of your loss function, the empirical risk. The gradient of your empirical risk exactly at the point that you are starting to departure, okay? So right now, I don't expect you to immediately see it. I'm going to show it for you. But this is the whole story. Like, if you find out why setting this mu to be the negative of the gradient, then when you replace it here, you're going to have the gradient descent algorithm. Clear? Any questions? No question? OK. So now, the next thing that I want to do is that to just go quickly over a bit of introduction, like basic things. I do know that most of you know this. I mean, all of you know this. But the point is that I need to just give you a bit of intuition when we go just expand the dimension, OK? So now, the first thing is derivative. I mean, anyone knows the definition of derivative, but let me just do it here. Yeah, a very hard quiz. Oops. OK. So if I have the function f of x, or f of w I have written there, being w, then what is the derivative? What is it? Don't be shy. I mean, I know it's very simple. Just say it. 1. So what is, I don't know, f of w squared? Then that is, what is it? 2w, yeah? So this dot that I put there, it means that I am taking the derivative. This guy is exactly the derivative that you have. And then when I put this w0 here, it means that I am calculating it at the exact point w0, right? So if I want to calculate, for example, the derivative here at point w0 equals by 2, then it's going to be f dot of 2. It's going to be what? 2 times 2 is going to be 4, yeah? So you got the notation, what I mean here, yeah? So that is the derivative, but the intuition behind derivative, what it means. It means that if, say, I am dealing with this function, so this is my function y equal by fw, so this is the function that I do have. This is a function of this weight. And now what I'm going to do, I'm going to move at point w0, I'm going to move with a tiny bit towards dw. Meaning that I start at this point, I just move very small step forward, yeah? Then I can get into a new point, which is not necessarily as small different from the initial y as what is for w, right? So it could change the value of y differently, right? And then basically, the ratio of this guy and this guy, when this dw is very, very small, is what you call it the derivative. And you do know that in one-dimensional case, it's basically the slope. Yeah? So the slope that passes exact or touches the curve at that particular point, that is your derivative. Now, what is the cool thing about the derivative is that if the derivative is positive, what do you conclude? The function is increasing, right? So if you want to increase the function, you should go in the direction of your derivative, so plus. For one-dimensional case, we have only two directions, plus, minus, right? So if I go in the direction plus, which is the sign of your derivative, then I'm going to increase my function. If I want to decrease my function, what should I do? Negative the direction of derivative, yeah? So I should go minus, right? Now, what if the derivative is negative? What does it mean? The function is decreasing. So if I go in the direction of derivative, which is now, if I just go in the direction of, if I go forward, the function is going to drop, and if I just go backward, the function is going to increase. Again, if I go in the direction of derivative, which is now this direction, If I go in this direction, the function is going to increase. If I go this direction, the function is going to decrease, yeah? So all the time, if I go in the direction of my derivative, I am going to increase my function. And if I go in the negative direction of my derivative, I'm going to decrease my function. So the first guess you could say is that mu should be proportional to the minus derivative of the function, right? Now, one question. When can this derivative be 0? When a function is, for example, minimum or maximum, right? So if the function is maximum, you can intuitively say that your function goes up and then touches the maximum and then goes down, right? Now, my function has a maximum, so let me look at this. So it means that when I start from one point, so say this is the maximum point, so you see this W max here, yeah? So when I am starting from any point before this W max, okay, and I move forward, what is the sign of derivative? It's positive, something positive, right? And then when I get to the maximum, it's 0. And what happens when I pass the maximum? Going to be negative, exactly. So you have first positive derivative, then it reduces to 0 gradually, and after that it is going to be negative, right? Now, if I want to draw here for you this function, which is the derivative of the same thing, f dot of w, okay? Derivative of the same thing here. So you told me before w max, I have something positive, right? So it's a kind of positive function. And then at this particular point, so this is w max, and then at this point it's going to be exactly 0, and after that it's going to be negative, right? Clear? Yeah. So at the maximum, that's going to be 0, and then after that, negative. Now, one question. If I take another derivative of this guy, what would be the sign of that derivative here? So you look at this f dot, again, as a function. If I take the derivative, is it at that point increasing or decreasing? It's decreasing. So the second derivative is going to be negative. Great. So if you have a maximum, then the derivative is 0, but your second derivative is going to be negative, right? Clear? Cool. Another point that we can have the derivative 0 is when we are dealing with a minimum. And this is what we are looking for. We want to end up there, yeah? But now let's look at this one again together. First of all, so this is one point. And that point is the point where your function is minimized. So W min there. And now I start from some point behind W min. Yeah? What is the sign of your derivative? It's negative, yeah? So it's somewhere here, right? So it's going to go up. And then at that particular point where the function is minimized, it's going to be 0, right? Because it gets negative values, it gradually increases to 0. And what happens after that? What is the derivative? Positive. So it's going to go up, right? Now, what about your function here, your derivative function? Is it increasing or decreasing? Is increasing, yeah? So again, if you have a minimum, you have a 0 derivative, but you have a positive second derivative. Clear? right? Now, another point that you can have is inflection point. Yeah? And the inflection point is this kind of point that you can see. So let me just draw it for you again. So I have this particular point, which is, okay, I can write it here, Wn. Yeah? So in this particular figure, okay, if I start from somewhere behind inflection point, what is the sign of my derivative? It's positive. The function is going up, right? So it's positive, it's something here. I do know that the derivative here is 0. What happens after I pass that point? It's again positive, right? So it's going to just go again up. So what would be this the second derivative here? It's 0. Great. So we could have inflection point. It's again 0. It has again 0 derivative, but the second derivative going to be 0. So basically, if you calculate the derivative of your function and you find out which points your function has 0 derivative, then you have 3 different possible candidates. The maximum one, the minimum one, and the inflection point. Yeah? And how you can decide which one that guy is, you can check the second derivative, right? Clear? So this is telling us if you're looking for the minimizer or maximizer of your function, you need to go ahead with derivative. Yeah? You need to deal with the derivative, right? Okay, so now this interesting point, the interesting story starts when we have a multidimensional function. And this is what we really have. So we don't have one particular w that we say, okay, we move in this direction, right? Forward, backward. We have a function which is a function of 2 different variables, for example, or more. And then the question is that can we extend all of these stories into that case? And the answer is yes, we can do this. How we can do it? So first of all, let me just define this partial derivative. So the partial derivative of a function is the derivative of this function with respect to the nth parameter here. Okay? And then many people show it like this. So the partial of f divided by partial of that particular variable. So let me just do it here once. We do another quiz together. So I have my f, and I have x and y. These are my variables. So I have x and y as my variables, and that is x, y plus x squared. Now, if I want to calculate the partial derivative of function f with respect to x, what it's going to be, can you tell me? Y plus 2x. Great. What about the partial derivative of f with respect to y? That is x, right? This guy now is treated as a constant, right? Because it does not have anything about y. So it's going to be x. Clear? Everybody's clear? What do I mean by partial derivative? Right? Now, I can extend the same idea that we had in the one-dimensional case in the multidimensional case. And what can I say? I can say, okay, say I start from one particular point w0 on this function. Yeah? So now what you can think of, like say we are in 2-dimensional space, so I can go anywhere on this plane, right? So it's not anymore a line that I can go forward, backward. I can go any direction. And at any point that I stop, then you take that point, you map it on the function which is passing here in the 3rd dimension, right? Now, what I'm going to do, I start at this point, and I'm going to take a very tiny step towards one direction. And how I show that one tiny direction, I show it by dw. So dw has a tiny element in this direction, tiny element in this direction, right? Or if we are in general n-dimensional space, in every dimension it has a tiny step, right? So now I have this tiny vector which is moving me in one direction. And now the question is that when I move in that direction, what's going to happen to the value of the function? So say at this point, this is the value of function, and then I move a bit forward, and then the value of function increases. What is this difference? Yeah? I want to know that. And then I can calculate it in this form. Yeah? So I can get the first partial derivative. I multiply it with the first element in that movement vector. The second partial derivative to the second element in the movement vector, and so on till the last guy. Yeah? So you get every partial derivative in different directions, and you get your movement element in that direction. You multiply them, you sum them up. It's going to give you the amount of change you're going to see in your function. Clear? Everybody's clear? Cool. So I can write it down in this form, and can you show it in form of a vector product? Is it a vector product? Yeah. It's an inner product, exactly. So what are the elements here in the first vector, for example, the row vector? The partial derivatives, yeah? What are the elements in the second vector? Are the elements of that tiny movement. So what I can say this guy is the inner product of that collection of partial derivatives with my movement vector, and what I call this guy, this new vector, this is what I call it, the gradient of my function. Right? Clear? So now in this example we had here, what is the gradient? Can you tell me? What is the gradient of that one? And I write it here because I don't have space. So I want to know what is, so my function, once again, my function, f of x and y, it was xy plus x squared, right? And now I want to just know what is my gradient, the gradient of function. What is it? Here it is y plus 2x. Exactly, this is the first element, because this is the derivative with respect to x, right? And what is the second element? It's x itself, exactly. So this is derivative with respect to y. Yeah? And you can expand it to the general n dimension. Clear? So that guy is the gradient. And the cool thing about the gradient is, again, like your derivative. You multiply it with your vector of movement, and then you get how much your function is going to change. Yeah? So it's the same thing. Now you should only think of vectorized world. Right? OK, so we can say that the change in the function is basically the inner product of our gradient and our movement vector. So that's cool. So we can just visualize it on this function. So the thing that I tried hard to show you here, you can see it in this slide. So we are at this particular point. So this is a two-dimensional world. So you basically have only two weights. And now you start from this particular point, which is your point W0, the point that you start. And then you move a very tiny bit in one direction, any direction that you want. Yeah? And if you want to know how much your function is changing, because your function was here when you were at this W0 point, and then it dropped into this point, right? Yeah? If you want to know what is this change, you basically just calculate the derivative or the gradient of your function, which is again a two-dimensional vector, because you take the derivative with respect to every single dimension, and then you calculate the inner product of these two guys. Clear? Everybody's clear? Yeah? Cool. OK. Great. So I can do, like, present everything in the space of my weight. How can I do it? Look at this guy. What I can do, I mean, this is a surface in dimension, yeah? And then I can cut that surface, right? And I can look at that surface from top, OK? And then that red dashed curve that you see here is basically what I see when I go top and look at that function after cutting it, yeah? Any points on that has the same altitude, right? Same value of y. So now, I was at particular point W0. I move in some direction. And if I calculate my gradient, this is going to be this direction. And then I calculate the inner product. And then I'm getting what is the value, the change on y-axis. Yeah? One key property that this gradient function has, you can simply show it. is that when you calculate the gradient at one particular point and you draw it, it's going to be orthogonal to the curve, to the contour that you have for your function. Yeah? I don't want you to just think about it right now because it's not really important, but just to know. Yeah? So it's always orthogonal to that contour. But anyways, the point is that if you want to calculate the difference of your function is that you go ahead and calculate the inner product, right? And since it's in 2 dimensions, we can still use what we know from vectors in 2 dimensions. And I can say that this difference, which is the inner product, I can write it down in form of the magnitude of this guy, the length of one vector, the length of the purple vector, times the length of the blue vector, dw, times the cos of the angle between them, right? So if you have 2 vectors, yeah, and you want to calculate the inner product in 2 dimensions, for example, you just look at the angle between them. So you're going to say the magnitude of the first guy multiplied with the magnitude of the second guy, and then times the cos of the angle between them, right? So everybody's clear? Yep.
I don't understand how that delta f is a vector. I thought that was just a magnitude, and then dw was
Delta f, no, it's a vector. Delta, you mean the gradient, yeah? Yeah, this one, right? So it's a vector.
then what's dw?
No, this is your gradient. Your gradient is a vector. You define it to be a vector, right?
Then what's dw? How is that a vector?
dw is your vector of movement. So here, what you say, you start at w0, right? Yeah. And if you want to move, then now you move in 2 directions. Yeah. So you would say, okay, I'm taking one step like this, but this one step is, I don't know, 0.7 step in this direction, 0. I don't know,
Yeah, so there's
7
directions,
this.
and then there's magnitude of the step. So
Yeah, of course.
So which is which? Which is the magnitude and which
Magnitude is this that I show with the norm. So this norm guy, this guy, this is the magnitude. Okay? So norm of any vector, I mean the magnitude of that. So, sorry, I think it has been a bit, has made you. So say I have this vector, say this is your dw. Yeah? So if you think of the 2-dimensional space, this is w1 and this is w2, right? And then this is w0, this is a vector still. So this is the first component of w0, so w01, and this guy is the second component, which is w02, right? And then when you say that my vector dw is in that direction, it means that you have a change here. This is what you call it dw0 and 1, so the first entry of your change. And this is the change in this direction, right? This is dw0 and 2. Yeah? So this is the amount of move you have on this axis. This is the amount of move you have on this axis, right? Yeah.
dw01 unit?
It's a unit. It's a number.
It's one?
It's
Unit vector?
no, it's not a unit vector. You choose it. You choose it very small, as small as you want.
Okay.
Yeah.
I thought it's a unit vector.
No, it's not a unit vector. It's a very small one, because if it is unit vector, but then your approximation is not a very good thing.
Then how do we choose it? Is it a fixed thing? Is it
No, it's not a fixed thing. You just think of it. So I mean, in theory, it should be the smallest ever possible. Yeah. So you take the limit when all of them go to 0, right? Yeah, this is the definition of the. So if you have a function like this, then you would say, okay, the derivative at this point is the value of function. So say this is w0. Then it's going to be w0 plus h. This is one step, or what I call the dw. Then this is going to be your function. This is the value of your function at w0 plus dw, right? And this is the value of function at point w0, right? And then what you're going to have, it's going to be W0 plus dW minus f at W0 divided by the size of this step, which is dW, right? And then you take the limit when it goes to 0, meaning that at this point you're just pushing it back as close as possible to this guy. But it would never be the guy itself. Yeah? And then you're going to get, so first you have this line, then you have the next line, and at the end you have the slope, right? So this is the same thing here in 2 dimensions. So you would say I move in a tiny direction, and then when I want to theoretically calculate the gradient, I should just send that tiny step towards 0.
Okay, so if we accept, if I understand now that the W0, 1, and 2 are a tiny fixed epsilon,
Yes.
and then there's something multiplied with that, and then it is y plus 2x and x.
Yeah, exactly.
So like if in that point W0, x is 5 and y is around 100, then
Yeah.
that's the magnitude multiplied with that tiny.
Yeah, sure. Then it's going to boom up. Yeah. So it means that like your function in one direction is smoothly going up, for example, when it's 2, and in the other direction, when you look at it, it's going hugely up. Yeah. Just think of this kind of function. Yeah. And then when you move here, your function is just going slightly up. But if you move here, then suddenly you just get top. Yeah. So any questions? So everybody's clear? Now, I want to calculate, once again, I want to calculate the change in my function. So what it would be? It would be the inner product of the gradient and the step size. And we discussed this is going to be the magnitude of your gradient times the magnitude of your movement times the angle between them. Right? Clear? Now, one question, if you just consider that. Now, this comes to your question. So if I think this is a very tiny movement whose length is fixed, yeah? So it means that I am here, and I want to just move very tiny bit, epsilon, but I have the choice to just move any direction, right? So I can move forward anywhere on the surface, but whatever direction I choose, I'm going to just move a tiny bit epsilon, right? Clear? So if that is the case, then the question is, which direction should I choose in order to make sure that after just moving that epsilon tiny bit of movement, I have the maximum amount of increase in my function. So what it should be? Look at this guy. So this guy is now constant, this dW. Yeah? This norm, the size of my movement is fixed. And the size of gradients, say for the moment, is fixed because I calculated it at that point. Now, the only thing that now plays role is this angle, right? And what should be this angle if I want that product to be maximum? It should be 0. It means that I should have theta equal by 0, or in other words, I should move exactly to the direction that the gradient is telling me, right? So it's the same thing as we had for one-dimensional function with, derivative.
Can you please repeat this?
Yeah. Say, if you look at this is the inner product, yeah? You can write it down. And this guy is your gradient, which is a kind of fixed vector at this point. So you have calculated this. You put W0 inside it, and then you get the vector. Now, the point is that you want to choose the movement, and you say that I do know that I want to move very tiny bit, but I have this degree of freedom to choose the direction that I want to go. Now the question is, which direction is the right direction if I want to increase my function the most? And what would be that? Is the direction where theta is 0, right? And theta is 0, it simply means that that direction, that blue vector, is exactly on my gradient vector. So the gradient is showing me the direction that I get the maximum increase in my function. Clear? Everybody's clear? Yep. Any questions? Now, since you don't have any question, I got a question. If I want to decrease my function now maximally, so I want to choose the direction where my function drops at most. Which direction is it? minus that one, yeah? So if I want to do that, I put that theta to be pi, right? So I put this blue line to be exactly the other direction of my gradient, yeah? Because that's going to make this change in the function the most negative possible, right? And this is the greatest drop in my value of the function. Meaning that if I want to just maximally decrease my function, I need to move exactly the opposite direction that my gradient is telling me, right? And if that was clear for you, then you're going to get, hopefully you got the idea what is gradient descent. So at every single point, if I do know the gradient, I just move exactly in the opposite direction of the gradient, and then the function is always going down, right? And I do know that among all directions that I could move, this is giving me the best drop, yeah? So I am going to get to the minimum much faster than any other direction, right? So this is why we say that the gradient direction is the steepest direction. So minus times gradient is the steepest direction that gives you the descent in your function. Steepest descent or gradient descent, this is the term that you use, right? Everybody's clear? Cool. So same thing we had with one-dimensional function, we have here with multi-dimensional function. And now the question is that there we said when the function is either minimum, maximum, or on the inflection point, we have derivative 0. Now, when do we have 0 gradient? And 0 gradient means every single entry on that function, on that vector, is 0. When do we have it? One case is exactly at the maximum again. Yeah? So you have your surface and it's going up. And this is this point where is the maximum of your function. Yeah? Top of the hill. Yeah? So anywhere around it, you start to move towards that top of the hill, you're always increasing. Yeah? When you step on the top of the hill, you're at the most toppest point. And then anywhere else you move, you always decrease, right? So that is the maximum. And before that, your gradient always telling you go that direction, then it's going to go backwards. So it's going to be, again, like your one-dimensional function, 0 at that point. Yeah? So this is one case that you could have. And it is not as easy as the one-dimensional case, but you can define something called Hessian matrix. And that Hessian matrix should be negative semi-definite in that point. I'm not going to open that up because we are not going to use second-order optimizers at all in this course. But just to give you a hint that same thing as that second-order derivative you have for a scalar function, you could define here as well. And then you can check whether that point is a maximizer or not by checking the definiteness of your Hessian matrix, right? Positive, exactly, yeah. That's going to be the minimum. So you could have a minimum, and again, the minimum is that when you are moving towards that, you're always decreasing, and when you departure from that, you're always increasing. Again, you're going to get your gradient 0, and then your Hessian matrix is going to be positive definite. Clear? And you could have, similar to inflection point that we had there, we could have one kind of popular other 0 gradient point, which is called the saddle point. And everybody's clear what is saddle, right? Saddle is the thing you put on the horse and you sit on it. Yeah? And how does it look like? So the saddle where I sit is like this, right? And if I just be exactly on the other direction, it's like this, right? So in one direction, it has a minimum. In the other direction, it has a maximum, right? Again, the gradient there is 0 because it makes sense. I mean, in one direction, you are touching the maximum. In other direction, you are touching the minimum. So in both directions, at that point, both partial derivatives are going to be 0. And your gradient is going to be 0. But that is not a maximum or minimum of your function. And you can simply, again, check it by checking the Hessian matrix. Everybody's clear?
Yeah, I'm sorry.
Yep.
Because it's a matrix, we call it PV, positive definite.
Positive definite, yes.
What's the reason? We didn't say that it's positive or
No, you cannot say. It's a matrix. So you calculate all the eigenvalues. If all of them are positive, then it's positive definite. If all of them are negative, it's negative definite. And if there is a change of sign, then it's going to be nor positive, neither definite. So this is the definition of the Hessian matrix. Yeah? And it basically includes all possible second order derivative of your function. So if your function is a function of n different parameters, then you're going to have n partial derivatives. And if you take partial derivative of every single of them, then for each of them, again, you have n other second order partial derivative, which is going to be n squared partial derivative. You can write it down in the form of a matrix. So n by n, but as I said, we are not going to use this matrix in the course. Yeah? Second order optimizers, we are not using it. Yes? Good. Because at the end of the day, I mean, if you want to compute that, you're going to see that this is not really feasible to compute it. You can compute it, but it is going to be very complex. I mean, even if we just use the gradient, we're still having trouble. Yeah? So we just calculate the gradient and move in the direction of gradient. And I'm going to show you that why we don't need to care about the converging point, because at the end of the day, we practically always end up with the minimum.
The math behind it, if we go with the gradient, which is first order derivative, we might end up at the local optimum. But if we go with Hessian matrix, which is harder computationally, we will always get to the global optimum. Is that
No, that's not the case. No. Now, the only thing that Hessian gives you is that it's gonna just estimate the better direction. So because when you have such a function, of course, I mean, at this point, gradient tells you go towards drop, yeah? But it's just pointing you towards the next minimum, yeah? But maybe if you have a kind of very changing function, Hessian could tell you what is the better direction, yeah? This is one point. The other thing is that if you have a, say, convex function, and if you can access Hessian, then that one basically tells you just take one step and you're at the minimum. Yeah? That's going to tell you the right step size. But the gradient descent doesn't give you that. So with gradient descent, you should be patient. You just drop one by one. Yeah? Yeah.
So Hessian has a better, bigger picture.
Sorry? Hessian has better picture, of course. If you have, I mean, theoretically, if you have any higher order information about the loss surface, then you basically have everything about the loss surface, right?
What about the saddle point? Wouldn't the gradient confuse the saddle point with the optimal point? But Hessian
It doesn't, the gradient. I mean, the gradient could confuse, but as I told you, if I can make it right now, this is never going to happen in practice. So it's almost zero probability that you end up with a saddle point if you use gradient descent. Yeah.
Yeah. I have two questions. In optimization, for the convex optimization, we have two methods. One of them are gradient descent, and the other one were Newton. Is this Hessian somehow
Newton direction, exactly.
Yeah, and why we didn't use the Newton in the machine learning?
Because this is very complex. Because you need to calculate n squared number of numbers, it is not possible. It's possible, but it's very hard. I mean, the training gonna get forever. Yeah. Okay. Everybody's clear about the gradient properties? Yeah? So, now, the moral of the story, as I told you, is that if I move in if I want to just find the right direction to move at every single point, in order to just drop my function maximally, the best direction is to just go for the negative of the gradient. And we can complete this algorithm that I initially showed you by just replacing, instead of that mu, the gradient itself, right? But if I want to move in that direction, I have the choice to just move very tiny bit, or I just take a very long step, right? And what should be that step? This is a good question, okay? That step is something that I right now showing it by eta, and this is what you probably have heard of, is the learning rate, yeah? So it's basically the step size that you want to move in the direction of gradient in order to just decrease your function. But as we're going to see in the next slide, it's not always good that you take any step size. Yeah? So you can simply think of it like this is your function. And then you start at this point. This says, OK, go that direction. But if you take a very, very long step, you could hit the other side of the function, yeah? Which is even more than your current point. Yeah? So that step size could not be as large as you want. And it makes sense because basically you just talked about tiny bit of movement at that point, yeah? When you were calculating the gradient. But at the other side, if I just take a very, very tiny bit of movement, then I need to be very patient till I get to the minimum. And if each of these steps take a very long time, I would not be happy to have tiny bit of a step, right? So it's a challenging question whether I should choose it large or short. And then we're going to see it through the lecture how we can manage it, handle it, okay? Now, that's basically this about the gradient descent, but if you got the idea of gradient descent, then the next thing that I want to give you an overview on is that what happens when we deal at the end of the day with practical loss functions or practical empirical rates. So things that we could have there, the first one is that we could have, one question that your friend already asked. So what would happen if I simply start just moving in the direction of the gradient or negative direction of the gradient? And I end up with a point where the gradient is 0. Yeah? Because as you can look at this gradient descent algorithm, if the gradient becomes 0, then my W does not get updated. This means that this delta is 0. This means that delta is not more than epsilon. The loop going to be over, right? So this algorithm is going to keep on, it keeps on going till it gets to some point where the gradient is 0, right? And then at that point, you're going to stop. But what if that is a maximum? What if that is a saddle point? Yeah? Long story short, it never happens in practice. Yeah? So we're going to see this has this property. The moment you get close to the maximum is the moment that you are just going to pass it. Or the same thing with a saddle point. So it's going to always keep you around the minimum. So that is not a big deal. So this is why we don't care anymore about the Hessian or anything else. This is one thing. The other thing is that at the end of the day, we need to calculate derivatives. Yeah? And that empirical risk depends on your neurons and then depends on your loss function. And what if your loss function or your neuron is not differentiable, meaning that you cannot calculate analytically the derivative at that point? What should we do? And then again, it has some sort of easy solution when the function is continuous, which we call it subgradient. If not, we can actually just deal with the sign. Okay? So that's something that I'm going to talk about on Tuesday. Okay? Everybody's clear? Any question? Great. So see you on Tuesday.